back to Quite Basic Math. I hope you've been enjoying every one of my videos. If you're yet to like my videos, subscribe and comment if you have questions for me or things that you want me to know. Alright, today we're talking about an operation with real number which we call surds. We're going to be looking at surds. Now, the concept of surds is such that we have something we call irrational numbers. Now, if you look up my videos where we talk about numbers, there's something we call irrational numbers. We said numbers can either be irrational, some numbers could be rational, some numbers could fall in the category of irrational. Now, surds are irrational numbers. They are irrational numbers. Why are they irrational? Now, for rational numbers, we said in numbers, if you check my video, you understand better on numbers. We said if you have a number, a real number, okay, we're looking at sets of real numbers now. So this is an operation with real numbers, not complex numbers. Now, if you have a set of rational numbers, we are talking about every number that can be expressed as a fraction of two integers, okay? We're looking at numbers that can be expressed as a fraction of two integers, okay? You have P and Q, they must both be integers. Now, if you can write an integer in form of a fraction, you have a rational number. Now, of course, you understand what irrational would be. So irrational is that you can't write the number in a fraction. You can't write two integers as a form of a fraction. And a good example of that are surds. Now, why is that so? An example of a surd is root 2. Root 2 is an example of a surd. There is no way you can write root 2 as a fraction of two integers. You might think root 2 can be written as root 2 over 1. Root 2 in itself, root 2 is approximately, okay, root 2 in itself is approximately 1.414 and, all of that. So this can't be written as a fraction. We have different types. So surds are irrational numbers. That you must first understand. For example, if I say root 4 is just 2. That's not a surd. So a surd is actually an irrational number. So example is root 2, root 3. The list is endless. These are examples of surds. Now we're looking at what we can do with surds. Just like we looked at complex numbers and what you can do with them. So let's look at this operation with real number, which is surds, and let's see what we can do with surds. Now there are some rules that guide surds. First off, let's look at surds as itself, how it relates to indices or how it relates to an index. Now if I say the root of a, for example, the root of a is actually saying a to the power of half. You must have probably come across this in indices. Now if I say the roots of say AB, for example, the root of AB is saying that according to indices, is saying AB raised to the power of half. I believe you got that. So these are surds. Not just root 3 is a surd. Okay, the cube root of 2 is also a surd. Why is this a surd? Because you can't write this as a fraction of two whole numbers. Please, this is cube root of 3, which means 2 to the power of 1 over 3. From the idea of indices, you should understand what this means. Alright, let's go back to our rules. So this is a basic idea. Well, I can't really call this a rule. This is a basic idea. Now let's look at an actual rule. Now you must take note that two surds can be added. Yes, you can add up two surds. Now if you add up two surds, say root A plus root B. Now if the surds can't be simplified further, your answer would be the same. Now you should take note that root A plus root B is not in any way equals to root A plus B. They can't share the same surd and then add up. This is not possible. However, if you are multiplying two surds, say root A times root B. Root A times root B is the same thing as root AB. This is a rule. This is valid. Okay? So if you have root A times root B, it can all share the same or common square root. Alright, so now if I have, the same goes for division. If I have root A over root B, okay, the same works. I can give it the entire square root and I have A over B inside. This also works. So you must take note of the fact that this would not hold, this will hold, and this as well will hold. I hope you're learning, okay? And let's move on. Now if you have, for example, two surds, let's just say something basic. Let's say root 2 times root 5. Now from what we said, you can have this to be root 2 times 5, right? And then this gives us the square root of 10. If you have something like root 10 over root 2, okay, they can share a common root, and then you have 10 over 2, and this gives us root of 5. So you should take note of all of this. All these guys will come in handy as we move on to bigger things. Okay, so let's look at some other things that you need to know about surds. Now there's something called simple surds. Okay, something called simple surds, and the idea of simple surds is that we have a surd. I've shown you examples of surds, root 2, root 3, and the likes. I've shown you this surds, right? Root 2, root 3, and the likes. So every surd can be reduced to its simplest form, except it's simple already. Now let me put them together. Now a simple surd is simply a surd that is written in its simplest form. I mean simple surd. So if you have a surd that is written in its simplest form, it's a simple surd. For example, root 2, it's simple. This can be reduced further. Root 3 is simple. Root 5 is simple. Root 7, even root 6 is simple. These are all simple surds. Now if I now say root 12, this is no longer a simple surd. Why is this not a simple surd? It's not simple because root 12 is not in its simplest form, and that takes us to what we call compound surds. Compound surds. Now if you have a compound surd is not a simple surd because you can reduce it further, you can simplify it further, right? Okay, so a compound surd like root 12, how do we simplify root 12? That takes us to having to understand the squares of some numbers. So I'm going to give you an assignment. If you don't already know, you are going to have to memorize some things. For example, to start with, memorize the square of numbers from 1 to 20 to help you. Let's go together, although let me give it to you. 1 squared, I'm sure you know, is 1. 2 squared, okay, is 4. Hi, this is simple, right? 3 squared is 9. I believe this is simple still. 4 squared is 16. All right, 5 squared is 25. Now this is important to be able to understand how to simplify compound surds. Okay, 6 squared is 36. 7 squared is 49. Okay, 8 squared is 64. 9 squared 81. 10 squared 100. Okay, I keep going. 11 squared, let me come here so it can be side by side. 11 squared, okay, is 121. Okay, 12 squared is 144. 13 squared is 169. 14 squared is 289. Sorry, not 289, that's a mistake, sorry. 14 squared is 196. 196. 15 squared is 225. 16 squared is 324. 17 squared is 361. 18 squared is sorry, or 18 squared, that's 8 times 8, 64. 19 squared, I think I've omitted something. 20 squared, because I'm trying, this is me trying to recall. I'm not using any calculator, just on my head. 20 squared is 400. Okay, 19 squared is 361. Right? Okay, sorry, I've seen where the mistake is. It's from here. This one's here, sorry, because I remember that I memorized this myself. I'm just trying to make sure to carry you along, to make you understand I'm not using any calculator at all. Okay, so 16 squared is 256. Sorry, 17 squared, 18 squared is 364. I think 324. Yeah, 17 squared is 289. Yes, and I think 18 squared is 324. Okay, let me confirm that because this is a place. I just want to make sure that I'm carrying you along to show you that you can memorize it yourself. Okay, I'm correct. 324. So this is the squares of numbers from 1 to 20. You need to know these 20 digits, these 20 squares at least, to be able to, in most cases, this would suffice for anything you want to reduce to its simple sword. So let's look at root 12. How do we reduce root 12 to its simple sword? Now you open a longer square root and you ask yourself this question. I have 12, right? Look at all these numbers. Which one of these numbers is closer to 12 such that you can multiply two numbers and it will give you 12? Now you're not just multiplying two numbers, you are multiplying a perfect square by another number which isn't perfect necessarily, okay? Because if you have a perfect and imperfect square, of course, you don't have a sword anymore multiplying. You get my point? So you're looking at the number 12 and you're asking yourself, what two numbers can I multiply? One of which must be a perfect square as I have here, and the other will be maybe a non-perfect square, okay? So if you look at 4, 4 seems to be the most sensible you can have here, because 9 times what will give you 12? That will not give you, that will be a decimal. I believe you understand what I'm saying. And none of these numbers here would give us what we want. So between 1 and 4, and 1 times 12 is not what you want. So if you look at 4 times what will give us 12? 3. 4 is a perfect square as you can see here. Then 3 is not a non-perfect square. Now according to our law, our rule of swords, that you can split this open just like we have here. You can go from left to right and right to left. Please take note of that. So if you are going from right to left now, you have roots 4 times 3. This can be root 4, okay, times root 3. The dot here is just saying multiplication. And root 4 we already know is 2 times this simple sword root 3. Can you see that we have been able to reduce a compound sword into a simple sword? So 2 root 3 is the simple sword form of the compound sword root 12. I take that again. 2 root 3, not the square root of 3, please. 2 root 3, a big 2 root a big 3, is actually the simple sword form of the compound sword root 12. Now if you are going from the simple sword form now back to your compound sword, all you need to do is open a bigger square root, square the number outside, okay, and multiply it by the number inside. Once you do that, that will take you back to your compound sword. I come again, square the number outside, multiply it by the number inside the square root. So you have root 4 times 3, which is actually square root of 12, and that takes your simple sword form back to your compound sword. All right, so let's proceed now. Let's proceed and take some more examples. What if I have root 24? You can see clearly that this is a compound sword. Why is this a compound sword? Because if you look at 24, definitely there are numbers. You can think of 4. If you look at 4 is a perfect square, right? And then 4 is a factor of 24. So 4 times what will give us 24? That is 6. 6 in itself is root 6. Don't forget, it said it's a simple sword. So 6 itself cannot be broken down further, but 4 can. So this works perfectly. So this is square root of 4 times square root of 6, and this will give us 2 root 6. So 2 root 6 is the simple sword form of the compound sword root 24. All right, and it goes on and on and on and on like that. Okay, another example. Let me use one more final example. What if you have roots, say root 32? If you have root 32 now, root 32 for example, can be broken down further. How? 16 comes to mind. 16 times 2. Somebody is thinking, you're thinking in your heart, how did I know it's 16? Why not 4? Fine, let's use 4. If you have root 32 and then you think of 4, right? 4 times what will give us 32? 8. But don't forget that 8 can still be broken down further. How? 8 is simply 4 times 2, right? So you can see that 8 in itself, it still carries the perfect square in it. And that is why root 16 times 2 is what gives us what we want. And this will be equal to square root of 16 times the square root of 2. And the square root of 16, as we know it, is 4 root 2. So 4 root 2 is the simple sword form of root 32. 4 root 2 is the simple sword form of root 32. Alright, I think that's all on converted simple sword to compound sword and compound swords to simple sword. So to convert 4 root 2 back to root 32, I've told you what to do. Square what is outside, multiply by what's inside. If I square 4, that will be 16, which will bring it inside. Then 16 times 2 is 32. The same goes for 2 root 6. What is outside is 2. Square it and bring it inside. So you have 4 times 6, and that is 24. Alright, let's go on and look at something we call conjugate of a sword. Let's look at the conjugate of a sword. Now, I would explain this for you first before we talk about how we can find or how we can to look at the conjugate of surd, or how it applies to solving surds. Now, the conjugate of a surd is basically that surd that when you multiply it by another surd, the surd whose conjugate you are trying to find, or you have written. What I'm saying is, if you have a surd root a, and of course the conjugate of root a is also root a, so you can see the point of the conjugate of the surd is that when you multiply it by the surd whose conjugate you have written, or you are multiplying it by, if that makes sense. Okay, so it will take out the surd and give you a rational number. Don't forget we said surd is irrational. So basically the conjugate, if you multiply the conjugate of a surd by that surd, what you are doing is you are converting from the irrational domain to your rational domain. That's what you are doing. You are converting from irrational to rational. So one of the things that multiplying a surd by its conjugate does for you is to cancel its irrationality. So look at root a. Root a is a surd, right? Why is it a surd? It's irrational, as you can see, even though there's no number attached to it. Now, if I multiply it by its conjugate, which is root a also, it will give me a. How? A raised to power half times a raised to power half. From the law of indices, they can share a common base, and I have half plus half, right? And half plus half is simply 1, which is just a. You can see that what it does is, if I multiply a surd by its conjugate, it actually deals with the irrationality of that surd. So you can say that a, which is the result of multiplying a surd by its conjugate, actually takes care of the square root. We do no longer have an irrationality situation. This now is rational. This now is rational. Okay, now let's look at something more technical. So like we said, now the conjugate of a surd actually takes irrational to rational domain. Now another thing we can look at is, what if you now have something like this, root 2 plus root 3. You know, for just a single surd, when I mean single, a surd that is not adding up to another thing. But if you have something like this, conjugate of this one will now become, okay, the conjugate of root 2 plus root 3 is simply root 2 minus root 3. So what you do is you just simply change the sign or the convention right in the middle of your surds. For example, if I have root 3 minus root 5, and I want to find the conjugate of this, the conjugate of this is simply root 3 plus root 5. So that's it. You just change what you have. But let's quickly see something. Let's see something. Now, if you multiply, you know, I said multiplying a conjugate by its surd, what actually it does is that it changes the domain from a rational domain to a rational domain. So let's imagine I actually multiply these two guys. Let's see the first one. So if I multiply root 2 plus root 3 by its conjugate, see what will happen now. If I multiply these two, what will I have? Root 2 times root 2. You know the way we multiply binomial factors. Root 2 times root 2, right? That's 2. Root 2 times minus root 2, that's minus root 2 root 3, plus root 3 root 2, that's plus root 3 root 2, minus root 3 root 3, right? And let's not forget that root 2 times root 3, that's root 6, plus root 3 times root 2, that's root 6, then minus root 9, which is just 3. Can you see that the irrational part is gone, and then what you have here will be negative 1. So what I'm saying in essence is that whenever you have a surd being multiplied by its conjugate, it transforms that surd from its irrational domain to a rational domain, or it transforms the irrationality of the surd or groups of surd to a rational domain. All right, so let's look at this second one too. So that just pinpoints what I'm trying to describe. So if I multiply root 3 minus root 5 by its conjugate, which is root 3 plus root 5, what will happen? You will see that this will give us 3. Root 3 times root 3 is 3, plus root 15, root 3 times root 5, minus root 15, root 5 times root 3, minus root 5 times root 5, which is just 5. So you see here again how this surd is eliminated. So you just have 3 minus 5, which is equals to negative 2. And this is both, or these are both rational numbers. Okay, Now let's proceed and see how to apply the conjugate of a surd in solving questions. Because you ask, what then do we use this for? Let me quickly show you what we use that for. Okay. Now, look at this. If you're solving questions that involves the division of two surds, root A, say root A over root B, right? Where they could be a group, okay? Let's say root B plus root C, something like this. So if you divide surds and you want to simplify them, what we do is we rationalize. So the concept of rationalization, let's look at the concept of rationalization. It simply helps in simplifying the division of surds. Rationalization. So if I have a surd, let's see examples, okay? Let's see examples. If I have, say, 2 over something simple, root 3 plus root 5, and you have to simplify this, all you need to do is to rationalize, you multiply the numerator and the denominator by the conjugate of the denominator. I take that again. To rationalize a surd, you in this case, because many people think that when you rationalize, you must always multiply you must always multiply the numerator and the denominator, that is what you have up and what you have down, by the conjugate of what you have down. It doesn't have to be by the conjugate of what you have down here, okay? But in most contexts, that is what would happen. But it doesn't have to be that. There are situations where you wouldn't do that, where it is actually the numerator's conjugate that you would work with. So let's look at this. But before we look at this, let me quickly show you a more simpler rationalization. Look at this. If I have 1 over root 2, this can actually be rationalized. How? You multiply the numerator and the denominator by the conjugate of your denominator. And the conjugate of the denominator is root 2. So this will now become root 2 over root 2 times root 2. And don't forget, root 2 times root 2 is simply 2. So 1 over root 2 and root 2 over root 2 are the same thing, just that we have rationalized. So if I rationalize these two, that is multiplying the numerator and denominator by the conjugate of the numerator, I will have back what I initially had, okay? And this will be 1 over root 2, back to what we have here. So that's the concept basically behind rationalization. So let's rationalize this together. That will be root 3 minus root 5 divided by root 3 minus root 5, okay? And this will be 2 into root 3 minus root 5, okay, over your denominator. Every time your inner product, what you have inside, would always go away. So basically, when you are multiplying itself by its conjugate, what you just need to do is multiply these guys, then these guys, okay? So that will be root 3 times root 3. Then what signs do you have in between them? Minus. Root 5 times root 5, that's just 5. So you don't waste your time having to open everything up. So this will be 2 into root 3 minus root 5 over negative 2. And this will now be 2 divides 2, that will be negative 1 into root 3 minus root 5. So the solution or the simplification of this surd, 2 over root 3 plus root 5, is simply root 5 minus root 3. If you open this bracket with minus 1, multiply minus 1, expand this, minus 1 times root 3 is minus root 3, minus 1 times minus root 5 is just root 5. So that is the rationalization of 2 over root 3 plus root 5. I hope you're following. Now let's go further. Let me give us one more example. If you have, say, root 2 plus root 3 over root 3 plus, or let's use negative this time, minus root 6, and you want to simplify this surd, all you need to do again, this will be times root 3 plus root 6. You multiply the numerator and denominator by the conjugate of your denominator. And once you do this, what would you have? You then have root 2 times root 3. That would be root 6, right? Root 2 times root 6, that's plus root 12. Then this, that will be plus 3. Then this, that will be plus root 18. Okay, what did I see? 12? Okay, yeah, root 2, root 12. All right, and then from there you divide by what you have in your denominator. That will just be 3 minus 6. I believe I've taught the trick. multiply this, then multiply this. So this will be root 6 plus root 12. Let's simplify all those compound surds so they are simple surds. Root 12 is the same thing as root 4 times 3. Hope you've not forgotten. Right, plus 3 plus root 18 is the same thing as root 9 times 2 all over negative 2. Okay, and then this would give us root 6 plus 2 root 3 plus 3 plus 3 root 2, okay, over negative 2. And this would be your final answer, because there's no way I don't see how you reduce this further in a sensible way. So this is your final answer. So the answer is just minus 1 over 2 into 3 plus 2 root 3 plus 3 root 2 plus root 6. Okay, and that will be your final answer. Okay, so let's go deeper and deeper and deeper, and let's look at a case. Let's look at another situation. If you have a situation where, say, you have something like this, 1 over root 2 plus root 3. If you have to simplify something like this, minus 1 over root 2 minus root 3. Now look at this question. You have to simplify this sort. The first thing first is, whenever you have two fractions being separated, this is a fraction, this is another fraction, being separated by an operator, okay, minus here, all you need to do is always consider the LCM. That's always the first step. So your LCM here will just be the product of this sort. So you have root 2 plus root 3 being multiplied by root 2 minus root 3. Now when you multiply these guys, you have after multiplying this, then you deal with your LCM on top. Okay, so what you have on top would be this divided by this, which is this guy, times 1. That will be root 2 minus root 3. Then this minus, open a bracket. Then this divided by this, you have this guy times 1. That will be root 2 plus root 3. Now if you open this bracket, you would have root 2 minus root 3 minus root 2 minus root 3 all over. Let's multiply this. I told you what this would always give to us, because basically this sort's conjugate is this, right? So if you multiply these guys, all you have is 2, right, minus 3. So this will be equals to root 2 minus root 2, that's gone, minus root 3 minus root 3, that will be negative 2 root 3 over minus 1. So this will give us 2 root 3. So the simplification of what you have here is simply 2 root 3. That takes us to an important rule. Whenever you have A of a root surd and then another C of root D, if you have a surd like this, okay, you can't simplify this further. However, if you have a surd like this plus C root B, where you have a common surd, you can always factorize, okay, such that you have A plus C all root B. Please take note of this. This is also an important rule that applies to surds. This is an important rule that applies to surd. Now let's go further, even a step further. Now that we have talked about rationalization, talked about simple surds, we've talked about compound surds, I've talked about how we can rationalize surds, right? How we can multiply surds, how we can add surds, subtract surds, and the likes. Let's now look at something that probably you might come across, or you should come across, in advanced mathematics. All what we have been doing has been pure mathematics from still high school or secondary school, or whatever it is being called, from where you're watching. Okay, now let's look at something much more technical, and that is solving surdical equations. So if you have an equation like this, for example, if you have 2 root x plus 3 equals to, say, root x. Now if you have to solve for x in a question like this, this is very simple. Let's look at surdical equations. How do we solve equations that involve surds? Now all you need to do here, you believe, is to collect like terms. You can bring this here. That will be negative root x equals to negative 3. Then here, from our rule of sort, this is 2 minus 1 root x equals to negative 3. And this will just be root x equals to negative 3. So to find x, what you do here is to square both sides. Squaring both sides actually eliminates the surd. In this case, the square root you have here. So when you square both sides, what happens is that this will give us x equals to minus 3 all squared. And the simple answer here will just be 9. So take note, for this question, x is 9. So let's check if this is correct. From the left hand side, okay, we have that root 2 root x plus 3. Is that not so? Then since we said x is 9, it means that 2 root 9 plus 3 is our left hand side. And what you have here would be 2 times 3 plus 3. And this is simply 6 plus 3, which is 9. Let's look at the right hand side. The right hand side says root x. The right hand side of the equation says root x. And we have said that x is 9, right? So if you have root 9, that will be 3. Okay, something is wrong here. This shouldn't be, sorry, it shouldn't be. Where did we go wrong? Something is wrong somewhere. Okay, so we brought root x here, and this is the negative side. So you have 2 root x minus root x. Then 2 root x minus this is root x equals minus 3. Okay, here is the problem. When you have root x equals to negative 3, this is a problem. The square root of a real number should not give you a negative number. Should not. Okay, so let's start this question. Okay, let's start this question. You can put in the comment section if you think you have an idea behind, because it's an example that I just formed of Ed. Okay, let's look at something much more understandable. Now if you have root x plus 1 equals to 5, something simple, and you have to find x in a surgical equation like this, you square both sides. Okay, if you square both sides, you have root x plus 1 all squared equals to 5 squared, and this takes away the roots. You have x plus 1, 5 squared is just 25, and x here then becomes 25 minus 1, which is 24. So let's check if this is correct. You can always check surgical equations. From the left hand side, we have root x plus 1. Since we said x is 24, that means you have root 24 plus 1, which is root 25. And root 25 is simply 5. So clearly this is correct, because our right hand side is also 5. So this is correct. So that's how to solve surgical equations. Now the other thing that you might need to also learn in sorts is what we call square roots of sorts. And we will discuss that in our next lesson. If you have the square roots of root 2 plus root 3, something like this, how do you solve this? So let's look at this. How do you solve the square root of sorts? We'll look at that in the next lesson. I hope you have been able to learn something. Bye for now.